Welcome everybody for the fractional calculus seminar. Today is a very special day. Today we have the 50th seminar within the fractional calculus seminar series, which has been running from last year. Today we have Professor Trifce Sandev, who is working as a research associate at the Research Center for Computer Science and Information Technology, Macedonia Academy of Sciences and Arts in Skopje. He holds a position as an associate professor of theoretical physics at the Institute of Physics, Faculty of Natural Sciences and Mathematics at SS Cyril and Methodius University in Skopje, and adjunct professor at the Department of Physics, Korea University in Seoul. After completing his PhD in theoretical physics in 2012 at SS Cyril and Methodius University in Skopje, he was a postdoctoral researcher and guest scientist at Max Planck Institute of Physics of Complex System in Dresden. He was awarded the Presidential Award for Best Young Scientist in Macedonia in 2011, the National Award Gosse del Chev in 2023 for his significant contribution to science in Macedonia since in 2022. As well as a research fellowship for experienced researchers for conducting research at the University of Boston in the period of 2020 to 2022 from Alexander von Humboldt Foundation. His main research interest is in stochastic process for complex systems, anonymous diffusion, random search, and stochastic resetting, as well as quantum mechanical systems with non-local interactions. We are very happy to have you here. You may please begin your talk.
Okay, thank you very much for your kind introduction, and thank you very much for inviting me to give this talk at your seminars. So today I will talk about some generalized heterogeneous diffusion and telegrapher processes on which we are working in the last maybe 5 years. And the presented material is in collaboration of many researchers from University of Potsdam, from Technion Israel, from Ben Gurion University, from Chennai, from Polish Academy of Sciences, Autonomous University of Barcelona, from the University of Olomouc, from Humboldt University, and this is our group in the group of Professor Ljubčo Kocarev at the Macedonian Academy of Sciences and Arts. So I will start with some introduction to the diffusion and telegrapher processes and their generalizations. And then I will talk about anomalous diffusion, some models of anomalous diffusion. And then I will present some recent results related to the first passage properties and stochastic resetting, on which we are working very actively in the last period. And at the end, I will give a summary and future directions. So diffusion in heterogeneous materials, like materials with impurities, amorphous media or fractal media, random heterogeneous structures and comps, etc., or weighted graphs and networks, the diffusion often becomes anomalous. I will explain you later what does it mean anomalous diffusion. And this anomalous diffusion appears due to several reasons. It can be because of memory effects or random potential acting in which the particle is bounded, or it can be the geometric constraints, some constraints in which the diffusion is conducted, or it can be because of the variation of the local diffusion coefficient in time and space, because in the heterogeneous materials the diffusion coefficient is not always a constant, but it can change from time to time, or it can change from one position to another position depending on the density or the heterogeneity of the environment, or it can be because of some velocity gradient that exists in the system in which the particle is moving. So as a normal diffusion, we define the process for which the mean square displacement is linear in time. But there are many processes that have different behavior of the mean square displacement. For example, if the mean square displacement has a power law dependence on time, then it is called anomalous diffusion. And this exponent mu is called anomalous diffusion exponent. If it is between 0 and 1, then we have subdiffusion. If it is equal to 1, then we have a normal diffusion. And if it is greater than 1, it is called superdiffusion. As a special case, if mu is equal to 2, this is the simply ballistic motion. And if mu is greater than 2, it is called like a hyperdiffusion, very fast diffusive process. So there are many systems in which this anomalous diffusion occur, and I will show you some models that we can use to describe this anomalous diffusive behavior. So anomalous diffusion is a generalization of the normal diffusion for the simple Brownian motion, which is the motion of massive particle immersed in some fluid, for example, liquid. And the mass of the immersed particle is much bigger than the mass of the molecules of the environment. And because of the interaction of the surrounding molecules on the massive particle, then it starts to move randomly. And this is known as a Brownian motion. And this Brownian motion can be described, for example, with this so-called Langevin equation, which is simply a second Newton law, but where the force acting on the particle, this is the friction force, this is the inertial term, and the force that acts on the particle is a random force. It's not some deterministic force like in the Newtonian equations, but it is a random force. And for example, if this frictional term is much higher than the inertial term, which is the case in many biological systems, then this is called overdamped Langevin equation. And for this random force, for example, can be a white noise. What does it mean, white noise? It means that the correlation of the noise is delta correlated. Why it is delta correlated? Because the interaction between the surrounding molecules and the massive particles is sudden. So we have a very sudden interaction between the massive particle and the surrounding molecules, and this is called fluctuation dissipation relation or fluctuation dissipation theorem. And if this fluctuation dissipation theorem is satisfied, then we call that the noise and the friction term and the noise have a same source, which means that there is a result of the interaction of the internal interaction in the system. But if this noise is not related to the friction term in the equation, then we call that the noise is external. We have some external noise, external force acting on the particle, and we can simulate this Langevin equation. And these are the trajectories of the Brownian motion. So we see that it can goes in different direction, and then we can do ensemble averaging of these trajectories, and we can find the mean square displacement. And the mean square displacement for this Brownian motion shows a linear dependence in time. So this is one equation to describe this Brownian motion for a normal diffusion. But we can also use the partial differential equation for the probability density function to find the particle at position x at time t. This is so-called diffusion equation that was derived by Einstein and Smoluchowski independently. And if we solve this equation, we will find that the solution is the Gaussian probability density function, which is shown on this graph here. And if we calculate the mean square displacement, we will see that again, the mean square displacement has a linear dependence in time, which means we have a normal diffusion, or we have another explanation of this Brownian motion, of this Brownian process. And there is also third way of describing this normal diffusion or a Brownian motion. It is called a random walk model, which means we have a lattice and the particle can go left to right or up and down with equal probability. After time step delta t, the particles goes in one of this direction randomly. And if we consider only one-dimensional case, only in x direction, then we can write the master equation for this so-called Markov process. And this master equation gives the probability density function of the particle at time t plus delta t, that the probability to find the particle at position j at time t plus delta t is there is a 1/2 probability that the particle will come from left and 1/2 probability that the particle will come from right, because we have a symmetric random process. And if we do a Taylor expansion, then we will find that the probability density function fulfills this diffusion equation, where the diffusion coefficient is defined like here. So these are three different ways to describe this Brownian motion for a normal Brownian, for a normal diffusive process. But what is unphysical in this diffusion equation is, if we analyze the probability density function, for example, here, we will see that at any time, for a very short time, there is a non-zero probability that the particle will be at infinity, which means that the particle can move with infinite velocity, which is not a case. That's why one can further introduce the so-called telegrapher's process, which is a simple process that the particle changes the direction of the velocity plus 1 minus 1. And if we consider this random process where this noise is not white noise like in the diffusion equation, but this is a so-called stationary dichotomic Markov process, which correlation is exponential, like this. Then, starting from this random process, we can derive the corresponding equation for the probability density function, and then we can find that the corresponding partial differential equation is the so-called telegrapher's equation. The difference between the telegrapher's and the diffusion equation is because here we have additional term where we have a second derivative in time in respect of the probability. And if tau is equal to 0, then we have simply diffusion equation. And the solution is given by this a bit more complicated form with Bessel functions. But if tau is very large, then this term, the first term, is dominant. The second term we can say that is very small, and then we will arrive to the wave equation. So the telegrapher's equation is something between the wave equation and the diffusion equation. And in the diffusion limit tau equal to 0, the mean square displacement again is has a linear dependence in time. But if tau is very large, then this is the wave limit. Then the mean square displacement has a t⁴ form, which is a ballistic motion. And if we plot, we see that the probability to find the particle at some position at some time t, it's bounded in some region which depends on the velocity of this jump process. So the particle at very short time cannot be found at infinity or at a very large distances, and that's why sometimes this telegrapher's equation is called like a relativistic diffusion equation. Like we have a limitation of the velocity of the moving of the movement of the particle. But when we have an anomalous diffusion, then we don't have a Markov process, which means that we don't have a process where the particle goes left or right with equal probability, and the distribution of the waiting times is exponential. But the particle can stay at some position very long time. For example, it moves from left to right and then stay for some time, and then goes right or left, but the time between the next movement can be shorter or longer. And if the distribution of this waiting time is for example, power law distribution, then we can derive the corresponding equation for the probability density function to find the particle at a position x at time t. And because of these waiting times, we will derive diffusion equation, but with a memory kernel here. If this memory kernel is a delta function, then this means that we have exponential distribution of waiting times, and this generalized wave equation will turn to the simple diffusion equation for a Brownian motion. But if we have some general form of the waiting time, which is given in the Laplace space like this, related to the memory kernel here, then the corresponding diffusion equation is this generalized diffusion equation with memory kernel. So we see that this is a non-Markov process, and differently to the Markov process in which you can find the position of the particle at the next time only by knowing the position of the particle in the previous time. Here you need to know all the states of the particle starting from 0 up to time t. That's why this is called non-Markovian process, and this process describes anomalous diffusive. This equation describes anomalous diffusive process. And like a special case for a Brownian motion, we have exponential waiting time. If we put this exponential waiting time and Gaussian distribution of the jumps of the particle, we put in this equation here, we will arrive to the standard diffusion equation. But if we consider a long-tailed waiting times, which means a power law waiting times of the particle can stay very long time at a given position, then we will derive this generalized diffusion equation with power law memory kernel. And if we put this power law memory kernel in the equation, we will see that this operator here, it's a fractional Caputo derivative, which is defined by this equation here. So in many papers you can find, for example, we generalize the process to fractional. Every law we can generalize to fractional equation just by changing the time derivative or space derivative with fractional derivative. But when you introduce some fractional equation, you need to justify this the usage of this fractional derivative. And here, this fractional derivative, Caputo fractional derivative, appear in the equation as a result of the power law waiting time of the particle in this continuous time random walk model. So it is it naturally appear in the final equation for the probability density function. And we can solve this probability this equation for this fractional diffusion equation by a so-called subordination approach. I will not go into details, but we can decompose the probability density function by using the known solution for the standard diffusion equation, which is a Gaussian distribution, and by introducing one probability density function, which is called subordination function, which describes the probability density to the particle to make exactly n steps up to time t. And we can describe this continuous time random walk process by using the Langevin equation, in which we can parameterize the time, the physical time, in terms of so-called operational time. And there is a relation between the waiting time and this subordination function. At the end, we can show that the solution of this fractional equation here, it's simply an subordination integral or decomposition integral of the probability density function for a simple diffusion equation, which is a Gaussian distribution, and this subordination function. And if we calculate the mean square displacement, we will find that the mean square displacement shows a power law dependence on time, which means that this fractional diffusion equation describes anomalous diffusive process. And as I said before, that anomalous diffusion in the system can appear due to memory, like in the previous case, where you should know all the position of the particle starting from time 0 up to time t, but also because of the geometric constraint of the environment in which the particle is moving. For example, if the particle performs free Brownian motion, then we will have, for example, here for two-dimensional Brownian motion, the corresponding equation is a diffusion equation in 2 dimensions. But what will happen if the particle moving along x direction can be trapped in y direction in these so-called fingers, which means that the particles, if it is trapped in this finger, it cannot jump in x direction, but it should go back to the backbone of this comp structure and continue to move in x direction, left or right. And because of these trapping events here can be considered like a waiting time of the particle. And if we have waiting time, some different than the exponential waiting time, then the corresponding process along this main channel, which is called backbone channel, it will be anomalous. The mean square displacement for a Brownian motion in such complex structure, the mean square displacement along the x direction will be proportional to t2 power 1/2, which means we have subdiffusion. And why is subdiffusion? Because the particle can be trapped in these fingers while moving along the backbone. And then instead of this equation for a free diffusion in 2 dimension, we will have a diffusion equation for a comp structure, which is modified by this delta function in front of the second derivative in x, which means that there is a diffusion along x direction only when y is equal to 0, when the particle will be at the backbone. Then we have a diffusion along the x direction. If y is different than 0, then the particle is in the finger and there is no diffusion in x direction. There is only diffusion in y direction. So we have some modification of this 2-dimensional diffusion equation. So this is another reason why anomalous diffusion can appear in some systems. And we can make simulation, for example, for more complex structure, which means that the particle moving along this main channel can be trapped in these fingers, but what will happen if there is additional fingers on the fingers, which means we have additional waiting time of the particle while moving in these additional fingers. And if we perform simulation about a Brownian motion in this 3-dimensional comp structure, we will see that the diffusion along z direction is a free diffusion. It's like a Brownian motion. The mean square displacement along z direction is proportional to t, which means we have a normal diffusion along z direction. But if we do simulation along y direction, we will see that there is a waiting time of the particle because the particle doesn't move along the y direction while it is in the fingers in z direction. And because of this waiting time, the mean square displacement along the y direction will be proportional to t to 1/2. And if we do simulation for the diffusion along the main channel, we will see that there are very long waiting times. Why we have a very long waiting times? Because the particle can be stuck in the fingers and additionally in the fingers of the fingers. And then the particle in x direction doesn't move. And because of this long waiting times, the corresponding mean square displacement along the x direction will be proportional to t to power 1/4, which means we have a subdiffusion. So this is another example of system with anomalous diffusion. But also this anomalous diffusion can be result as a position non-constant diffusion coefficient. What will happen if we have a system in which the diffusion coefficient of the particle is different in different position of the system? And this is a case of a heterogeneous materials in which we don't have a homogeneous environment in which all the time we have a constant diffusion coefficient, but the diffusion coefficient changes with the position. And there are many systems that shows this variation of the local diffusion coefficient, and we can describe these anomalous processes by using generalized or so-called heterogeneous diffusion equations. And there are many examples in the literature of application of this diffusion equation with position-dependent diffusion coefficient. And this is one example of a crowded cell. And if you track the movement of this fluorescent protein, like here, in this heterogeneous environment, then the diffusion coefficient in different position of this system, it will be different. So it will depend on X or X and Y or on the R vector. And this is another system, for example, movement of some person here in the Sao Paulo underground station. So the movement of a person which is close to the stairs, it will be faster, but when it is in this very dense environment, then it will move slowly. So these are two systems in which we have this heterogeneous diffusive process. And this process can be described by this equation. So it's a diffusion equation, but here we see that the diffusion coefficient depends on X. If alpha is equal to 0, then this and this disappears. We will arrive to the standard diffusion equation with constant diffusion coefficient. But if we have this variation of the diffusion equation, like in cytoplasm of a mammalian cell, then we should use this heterogeneous diffusion equation in order to describe this anomalous diffusive behavior. And we can use Langevin equation approach, which means that now we have diffusion coefficient which depends on the position. And here we have a white noise. And because this position-dependent diffusion coefficient, the white noise is not additive, it is multiplicative noise in this case. And there are different interpretations of heterogeneous diffusion equation, but I don't want to go in details. If you have some questions at the end, I will try to answer. So it depends how you integrate this Langevin equation, and the corresponding diffusion equation can have additional terms, additional drift terms, depending on the interpretation of this Langevin equation, of this multiplicative noise. So there are three different interpretations, like E2 interpretation. This one is Stratonovich interpretations, and there is a third one, Hengi-Klimontovich interpretations. And we can solve this equation, and we will find that the corresponding solution is given by this relation here. And if we find the mean square displacement, we will see that it is proportional to t to power p, where p is equal to over 2 minus alpha. So depending on this alpha, which should be less than 2 in order to have a solution of this equation, alpha should be less than 2. Then if alpha is less than 0, we have a subdiffusion. If alpha is equal to 0, we have a normal diffusion, because the equation is a normal, is a standard diffusion equation. If alpha is between 0 and 1, then we will have a super diffusion. If alpha is equal to 1, we will have ballistic motion. If alpha is between 1 and 2, then we will have a hyper diffusion. And the special case alpha equal to, this will need a different treatment of this equation, but this is known a process in economy, like in the Black-Scholes model for the income dynamics, stock prices. This is called geometric Brownian motion when alpha is equal to 2. And the corresponding solution then of this equation will be a log normal distribution. This is a very known model in finance, in economy. And what will happen if we have a telegrapher's process, but in which we have a position-dependent velocity, which means that the velocity is not constant, it's not changing its direction from +1 to -1, but it changes the direction, but the speed depends on the position. And then if we write this stochastic equation for this multiplicative dichotomic noise, as in the standard telegrapher's equation, it is a exponentially correlated noise, then we can derive the corresponding equation for the probability density function, and we will arrive to this equation, which is a telegrapher's equation, because we have this additional term with the second derivative in time, but then we have this position-dependent diffusion coefficient, which is related to the position-dependent velocity of the particle. And then we can solve this equation. It's a bit more complicated than the case for the standard telegrapher's process. And we can plot the solution, and we will see that the particle cannot be far away from the origin for a very, very short time. So we have a limitation of the velocity of the particle, which is not the case for the diffusion equation. And now this heterogeneous diffusion and telegrapher's process, we can further generalize. For example, the particle moving in a heterogeneous medium, but it can be trapped and it can stay for a long time at some position, like in the continuous time random walk model. And if we have these trapping events and waiting time of the particle, then we can derive the corresponding fractional heterogeneous telegrapher's equation. So we have a multiplicative process with a random velocity, but we have additional waiting time of the particle. And the resulting, this process can be described by this so-called fractional heterogeneous telegrapher's equation, because instead of this first derivative, we have a fractional derivative in time. And because of this second derivative, we have a fractional derivative in time where the order is 2 mu. And we can analyze this equation, we can solve the equation, we can calculate the mean square displacement, and we will see that in the short time, the particle has one diffusive behavior. In long time limit, it has another diffusive behavior, depending on this parameter mu, which is related to the waiting time of the particle, and this parameter alpha, which is related to the heterogeneity of the environment, the form of the velocity, position-dependent velocity. And we can write this diagram here, and we can find the regions in which we can observe transition from subdiffusion to subdiffusion. If alpha and mu belongs to this region here, we will have superdiffusion to subdiffusion. If the parameters are on this line, then we will have transition from normal diffusion to subdiffusion. Then we can have a transition from ballistic motion to normal diffusion, from hyperdiffusion to superdiffusion, from hyperdiffusion to ballistic motion, and from hyperdiffusion to hyperdiffusion. So we have a not so complicated process, but the resulting behavior of the particle is very rich. So just with changing of this parameter mu and alpha, we can observe different anomalous diffusive behavior and transition from one diffusion behavior to another in the long time limit. And I mentioned in some of the previous slides that also anomalous diffusion, we can observe anomalous diffusion because of a velocity gradient in the system. And this is called a shear-driven diffusion, which is a form of a turbulent diffusion of a diffusing impurity in a stream with velocity gradient. And it is nothing else but two-dimensional Brownian motion if we don't consider the last term. So this is the differential equation for a Brownian motion in two dimension. But if we have additional this velocity gradient here, which is presented on the plot here, which means that the velocity gradient depends. We have different external force acting on the particle on different position of the particle along the y direction. And if we add this additional term here, we can write the corresponding Lagrangian equations for this two-dimensional motion. We can perform simulations and we can find the mean square displacement and the variance. And we will see that for this two-dimensional Brownian motion in a linear shear flow, the mean square displacement at short times shows normal diffusive behavior. And in the long time, we have a hyperdiffusion where the exponent is equal to 3. And why this is a transition from normal diffusion to this hyperdiffusion? Because for short time, the particle doesn't feel the velocity gradient, and the mean square displacement, the particle will act like a Brownian particle and the normal diffusive process. We will have a mean square displacement which is proportional to time. But for long time, because of this velocity gradient, the mean square displacement will be T⁵, and this is a form of a so-called turbulent diffusion. And we can further generalize this two-dimensional Brownian motion in a linear shear flow if we introduce this waiting time of the particle. The particle can be tracked in some position, and these circles have different radius here, and different radius means different waiting times. And if we have a different waiting times, starting from the previous equations, Lagrangian equations, and this so-called Fokker-Planck equation for the probability density function, we can derive the corresponding equation for this anomalous diffusive process. So then, because of the waiting time, we will have, instead of a first derivative in time, we will have a Caputo derivative in time. And then if we calculate the mean square displacement, we will see that for short time, it is T⁵mu. And because mu is between 0 and 1, in short time, we will have subdiffusive behavior. But for large time, we will have the anomalous diffusion exponent will be 3mu. And depending on mu, if it is between 0 and 1/3, or between 1/3 and 2/3, or 2/3 and 1, we will have transition from subdiffusion to, it can be to subdiffusion, or to normal diffusion, or to superdiffusion, or to ballistic motion too. So we will have a different behaviors of the particle depending on the waiting time of the particle in this Brownian, two-dimensional Brownian motion in a linear shear flow. So these are different models which we can use to describe this anomalous diffusive behavior. And now I will give you some results related to the first passage properties and stochastic resetting, because these random processes are very useful in the random search. For example, in animals searching for food, or human behavior, human search, or computer search. we can use such diffusive processes to find, for example, optimal search strategy, which means what will be the corresponding search process in order to find the target for a shortest time. So then, and stochastic resetting, which is a very popular mechanism in the last 10 years, and it was considered like one of the hottest topic in non-equilibrium statistical physics in the last 10 years. So, as I said, this random processes describing anomalous diffusion or normal diffusion can be used in human searching, in foraging dynamics, when we have some animal searching for food, and after some time, if the animal doesn't find the food, it comes back to the nest and then start the search again. So it means that the position of the searcher is reset to the initial position. It can be a computer search, or it can be an economy, for example, in this stock prices. If we have some company bankruptcy or crashes, then we will have a sudden drop of these stock prices, and this can be considered like a resetting event. And in the last years, also this stochastic resetting is very popular also in quantum systems. First, I will show you a simple Brownian search. So we have a Brownian particle starting from position x0 and start moving left or right. And what is the probability to hit the target, which is located at x equal to 0? Then, starting from the Fokker-Planck or the diffusion equation, we can write the corresponding backward equation for the survival probability, and we can solve this, which means that the probability the particle to survive, which means that the particle will be like killed when it reaches the target. And we can calculate this survival probability, and from this survival probability, we can calculate the mean first passage time. So we will have an ensemble of particles starting from x0. We perform simulation, and we detect the times when the particle will hit the target. And because we have a random motion, random Brownian motion, the target will be hit at different times. But there is a probability that at least one particle will never hit the target, because it starts to move in a wrong direction. It will never hit the target. And when we will find the mean first passage time, we will see that it diverges. And because of this phenomena, we will see later, it is introduced this stochastic resetting, because we want this mean first passage time. When you have a random search process, you want the mean first passage time to be a finite. So to finite time to find the particles, to find the target. And in this case of a simple Brownian motion, the first passage time density is a Lévy-Smirnov distribution, and if we calculate this mean first passage time, it is infinite. And if we do the same, like we have a random search process described by the telegraphers, heterogeneous telegraphers equation. From the corresponding equation for the probability density function, we can integrate and find the corresponding equation for the survival probability. And then we can calculate the mean first passage time, the first passage time density, and we will see that the mean first passage time density also diverges for the heterogeneous diffusion and telegraphers processes. And that's why we should introduce stochastic resetting in order this mean first passage time to become finite. And the stochastic resetting can be described. So if we have a simple Brownian motion, we have this trajectory on the first graph. But if we have a Brownian motion with exponential distribution of resetting, then the particle performs Brownian motion, and after some time it is reset to the initial position, and the particle starts to move again from the initial position. It performs a Brownian motion, it is reset again to the initial position. And we can find the corresponding equation for this Brownian motion with resetting, and it can be described by this renewal equation. There is a more generalized form of this equation, depending on the distribution of the resetting time. But if we have an exponential distribution of resetting, then the corresponding equation for the probability density function in case of resetting is given by this equation, which means that we can find the probability density function in case of resetting if we know the probability density function without resetting. And for a Brownian simple Brownian motion, this P0 is a Gaussian distribution. And the distribution of this Brownian motion in case of resetting is simply if we exchange here in the equation a Gaussian probability density function, and we can find the corresponding probability density function in case of resetting. And then in the long time limit, we will see that the system will approach a non-equilibrium stationary state. And the form of this distribution is Laplacian. So if we don't have resetting, the corresponding probability density function is a Gaussian. But if we have resetting, in the long time limit, the probability density function is Laplacian. And if you calculate the mean square displacement, we can find exact form of the mean square displacement. And in the short time limit, it is proportional to time t. Why it is proportional to time t? Because the particle, for a very short time, there is no resetting event. The particle performs free Brownian motion. But if we have an exponential distribution of resetting in the long time limit, the mean square displacement will saturate to some value, which depends on the diffusion coefficient and the resetting rate are here. This simple diffusion process with resetting shows a very rich behavior because you can further analyze the solution and you will find that there is a second order dynamical phase transition in this process, which means if the particle is in this region here or here, the particle is not relaxed to the stationary state, but it is in a transient region. And if it is in this region here, the particle is already relaxed to the stationary state. And if we write the corresponding equation for the survival probability, which means we want to find the mean first passage time to hit the target in case of Brownian motion with resetting, we will see that the mean first passage time it's for different resetting rates, it's a finite, which means that there is some optimal resetting rate at which the mean first passage time is minimal. So if you know the process, you know the search process with which equation it is described, you can tune the resetting rate in order to make the mean first passage time minimal. And this is a very interesting behavior of random search processes in case of resetting. And then we can do this for a anomalous diffusive search in case of resetting, where we have anomalous behavior with these waiting times here, but after some time you reset the particle to the initial position, and we will observe also in these anomalous diffusive processes, which are described with diffusion equation with the memory kernel, that the mean first passage time becomes finite if we introduce a resetting in the system, and this makes this process useful in the optimal search strategies. And we can do this, for example, for the heterogeneous diffusive process or heterogeneous telegrapher's process. and we can calculate exactly the mean first passage time. We will see that the mean first passage time is finite in case of resetting, and that there is an optimal resetting rate at which the mean first passage time is minimal. And in this heterogeneous telegrapher's process, this phase diagram is much more complicated because we have interplay between heterogeneity of the environment, the memory of the system, and resetting. So in the simple Brownian motion with resetting, we have this case here, where we have a phase transition from transient regime to non-equilibrium stationary state. But in case of a heterogeneous diffusion and telegrapher's process, with these waiting times, we have a richer behavior in this phase diagram. And as I said before, the mean first passage time, for example, for the fractional telegrapher's process, we can find that in case of resetting, the system approaches a non-equilibrium stationary state, and that the mean first passage time from infinite becomes finite due to the resetting. And here, for different parameters of the system, we see that there is an optimal resetting rate at which the mean first passage time is minimal. So by knowing the process, you can choose the resetting rate for which the mean first passage time is minimal, and this process you can use as a search strategy in some random search process. This is for the fractional heterogeneous telegrapher's process. We also observe non-equilibrium stationary state, and in the long time limit, the mean square displacement saturates, which means that in the short time limit, we have the same behavior like in the system without resetting, and in the long time limit, we have a saturation of the mean square displacement because of this resetting events, and because the particle approaches a non-equilibrium stationary state. And then we can calculate the mean first passage time. Again, for this fractional telegrapher's equation and fractional heterogeneous diffusion equation, we can choose appropriate resetting rate to make the mean first passage time minimal. And as a summary, in this presentation, I try to show how the standard diffusion and telegrapher's equation can be generalized to fractional diffusion and telegrapher's equation. So these generalizations are not artificial, which means that I didn't start from the fractional diffusion or fractional telegrapher's equation. I started from some random walk model with waiting times, with geometric constraints, or with heterogeneity in the environment. And from this random process in such heterogeneous environment, we can derive the corresponding equation, diffusion telegrapher's equation, with fractional derivatives. So the fractional derivatives appears naturally in the system. They are not introduced artificially in the equations. And in this presentation, I try to give examples how these anomalous diffusive processes can be described with different models, with continuous time random walk models, or with random processes with position-dependent diffusion, or coefficient or position-dependent velocity. And these models shows a very rich behavior. And if we introduce the stochastic resetting in these random processes, in the long time limit, the system approaches a non-equilibrium stationary state because of the resetting, and that the mean first passage time becomes minimal, and that there is a optimal resetting rate at which the mean first passage time is minimal. And these are some of our results that are published related to these random searches and stochastic resetting and diffusion processes with resetting, and it is a very active field in the last years. For example, in this paper, we use this resetting event for a particle embedded in a viscoelastic bed, and we are happy that our paper was on the cover page of the March issue of the journal Chaos. And this shared-driven anomalous diffusion that I show you, it was selected like a feature paper in physics of fluid, and in other papers, for example, in this paper, we applied this stochastic resetting in some economic model of a Black-Scholes model, which is a geometric Brownian motion with resetting. And we use this stochastic resetting to explain the income dynamics in USA in the last maybe 50 years. We had the data for the last 50 years for the income dynamics in US, and you can see some drop of the income in US because of economic crisis or because of COVID. And these events we can consider like a stochastic resetting in the income. And then we can apply this geometric Brownian motion with stochastic resetting to explain this data. And we can apply these random search strategies in different processes. And like future projects, we will analyze the so-called herding model and voter models. These are models for social behavior or the human behavior. And if we analyze the corresponding equation, it is nothing else but a diffusion equation with position-dependent diffusion coefficient and position-dependent external force. And we will try to analyze such models to apply to real data and maybe to introduce stochastic resetting and to see what will be the corresponding behavior. And the share-driven anomalous diffusion in case of resetting, we will try to find the first passage properties, the mean first passage time, and if there is an optimal resetting rate for which we can make this mean first passage time minimal. And maybe for some groups that are working on experiment, it will be nice to demonstrate these theoretical results with resetting for a heterogeneous diffusion or heterogeneous telegrapher's process, because for a simple diffusion process, it is already done. For example, movement of a colloidal particle in a laboratory setup using optical tweezers or laser traps, which means we have a colloidal particles that performs a simple Brownian motion, and then by these optical tweezers or laser traps, the particle in the system you introduced confining potential, and because of this confining potential, you bring back the particle to the initial position, and this then you can switch off this confining potential, and the particle will start to move again freely like a normal diffusion, and then you switched on the potential, and this switching off and on of the potential can mimic this resetting of the particle to the initial position. So it will be nice these experiments to be done for more systems like heterogeneous systems in which the diffusion coefficient is not constant. So these are some works that we published in the last 5 years related to these random searches, heterogeneous diffusion, and stochastic resetting. And with this, I would like to finish my talk, and thank you very much for your attention.
That was a very informative talk. For questions, please raise your hand. I'll call out your name as they appear on my screen. I believe Nikolai has a question. Nikolai, do you have a question?
My question is about subordination. For a standard diffusion model, when you replaced time derivatives into derivative in computer sense, then it means that instead of time, you have to substitute inverse stable subordinator, and you had shown me. You have to consider a stable subordinator, inverse function, what we call first passage time process, and substitute. But for hyperbolic diffusion, when you have second derivative in x. In your slides it was function h of tx for this subordination. What do you know this function exactly? What is the function? What is the process you have to? Yes, somewhere in the middle. Go down. So down. No, before. Yes, down. Maybe. I mean.
Yes, here.
Yes, exactly. What is the function h of ut? Do you know
Yeah.
exactly for a hyperbolic case?
Yeah, this is, as you said, that you have a alpha Lévy stable subordinator, or in this case, mu Lévy stable subordinator. If you want to go from the normal diffusion to fractional diffusion equation with Caputo fractional derivative.
No, but
if
that's when
you,
there is no second derivative in time, when it's without hyperbolic case,
yeah,
it's parabolic case. But
yes, but if you have a telegrapher's process,
yes,
and you do the same, then in the corresponding equation for the probability density function, you will have a Caputo fractional derivative of order mu and Caputo fractional derivative of order 2 mu. So if you
yes, I understood, but I mean, why you can do the same? I mean, it's not clear.
It's a standard procedure. So if you start from the telegrapher's equation and introduce.
So if you can, okay, telegraph equation has stochastic representation integral from 0 to t minus 1 to the power of Poisson process, and that's a stochastic representation. When you have to substitute inverse stable subordinator in integral or in Poisson process, where is the substitution of inverse stable subordinator?
So you do the same in analogy of the diffusion you can do for the telegrapher's equation. And I can show you, I can send you some of the papers in which we derive this.
Please. I will send you a mail after this talk.
Yes, please send me an email. And if you introduce this Lévy stable subordinator, then you will find the telegrapher's equation in which the fractional orders are of order mu and 2 mu.
Yeah, but if you consider, suppose there is no first derivative in time, and that's a wave equation. In this case, when you try to write stochastic representation, you have absolutely different picture. It's a D'Alembert formula in which you have substitute some complicated paper of Meyer-Schartz and others.
Right.
But so it means that at least in some partial cases, this doesn't look like similar to diffusion case.
For the telegrapher's equation, you can use this subordination approach. So please send me an email and I can.
Okay, I will send you. Sorry, it's probably a very local discussion.
Yes.
Okay, thank you, Pavan. Yeah.
Thank you very much.
Does anybody have another question? You can unmute your mic and go ahead.
Hi.
Yes, go ahead.
Thank you for the nice presentation. When describing this resetting procedure, maybe my understanding was not correct, because my understanding was that somehow for instance, in this foraging search that you mentioned, these examples that you gave, so the animal or the process, essentially you start, you are in a given stage of the search, and then you return to your original state, right?
Right.
So somehow for me, this would be like a cyclic trajectory, if I am understanding that from the correct point of view. But I could not see that cyclic behavior in the way you describe it. Maybe could you comment on that, please?
Thank you for the question. So it's not a cyclic behavior, because you have, for example, normal diffusion with resetting. Usually, the simplest case is when you consider exponential resetting. And in this case, everything you can find exactly. This process is not like very physical, because you reset the particle immediately to the initial state. But for many systems, you can use such model, which means that the time at which you reset the particle, this time belongs to some resetting distribution of the resetting events. So you don't have, and because this Brownian motion is a random process, the process can go in the particle can go left or right. You don't have all the time the same situation, which means when you reset the particle at the beginning, it doesn't start to move to the same trajectory. The trajectory is always different. So you don't repeat all the time the same trajectory after your resetting. It's
Yes, sorry, maybe I didn't explain myself. So it's like each time you perform a search, you return to your original position, right? That's what I meant by cyclic. Maybe it's or closed trajectory in each step of the searching process. That's what I meant by, maybe it was not correctly stated like cyclic, but
and the result of this stochastic resetting is that the particle reaches a non-equilibrium stationary state, which means that in the long time limit, the particle approaches some stationary state. But why it is called non-equilibrium? It is called non-equilibrium because all the time the particle is reset to the initial position and you have a probability at the origin. So that's why it is called non-equilibrium stationary state. And if you calculate the mean square displacement of this process, then you will see that in the long time limit, the mean square displacement saturates. Because of this resetting, the particle can now go far away from the origin. But when you do an ensemble averaging, the mean square displacement will be saturated depending on the diffusion coefficient and resetting rate. And it is important that the mean first passage time becomes finite, because when you reset the particle, all the particles that go in wrong direction you reset, and then after the resetting, the particle can go in the right direction. And that's why the mean first passage time becomes finite. So this was the idea, and then many researchers started to use this idea of stochastic resetting, that the mean first passage time for a Brownian particle, which is infinite, you make it finite simply by this stochastic resetting.
Thank you.
Does anybody have more questions? You can unmute your mic.
Maybe can I ask also another question?
Please.
Yes, maybe it's related to the previous question by Nikolai, I guess, was the person who asked you. When you have this subordination process, so essentially you are separating the variables, the time and space variables by this process, by this procedure. So, I mean, from the point of view of the results, I mean, they seem to be very nice, but to guarantee, and maybe this is related, I mean, the structure of the equation changes from hyperbolic to parabolic. So when you go into these two different regimes, so the physical behavior can indeed change. So there are not really any additional constrictions when you go from one regime to the other when using this subordination process. In the way that this h of t, this h function is behaving.
Yes, this is a very good question. So depending on the waiting time of the particle, then you will have a different subordination function. And because the solution of this new process, of the probability density function of this new process, is a subordination integral of the probability density function of a simple, for example, Brownian motion, and this subordination function. This subordination function should be non-negative. And it will be non-negative if in Laplace space, if you analyze it in the Laplace space, it should be a completely monotone function. And by analyzing the subordination function in Laplace space, then you will find the restriction of this memory kernel in this generalized equation that I show you one of the first slides. So we have a memory kernel here which appears due to the waiting time. And but with this subordination approach and by the analysis of this subordination function, you will find the restriction of the form of this memory kernel here. So not every memory kernel can be used to describe some kind of anomalous diffusion. Because if you put some memory kernel, then you will find that the subordination function and the corresponding probability density function will be negative. So you should have a restriction that the probability density function is always non-zero. It's a positive function. And this is also some cases in some literature, you just generalize this to fractional equations and you say that you describe diffusion. And when you analyze the subordination function, you will see that it is a negative, which means it doesn't represent a good stochastic process. So there are some restrictions on this memory kernel, which form it can have.
Thank you very much.
May I have a question? Can I do it?
Yes, please.
I'm Fabrizio Cinque. First of all, thank you very much for the interesting presentation. And again, regarding this memory kernel, I would have just a question. If you tried other kind of kernels more than the one you showed, and I would also have a second question. I will just ask it. If you have considered the case in which the resetting is not leading the particle to the origin, but to, I don't know, to inside a certain region or anyway, a random location. If it's still the expected value, if the expected time is still finite, or it may explode again.
Yeah.
Thank you.
So the first question was about the form of the memory kernel. Which form can have?
No, yeah, I was wondering if you tried other kind of forms.
Yeah, you can try other forms of the memory kernel, but as I already said before, that this memory kernel should satisfy some, I don't remember if, for example, by analysis of the subordination function in Laplace space, you will find some restriction of the memory kernel. For example, that the Laplace transform of the memory kernel should be completely monotone function. And the Laplace form...
Can you answer this question? Sorry. Actually, there is a Lévy process which is called subordinators, and there is a Lévy measure of this. And this memory kernel is a simply tail of the Lévy measure of any subordinator. That's a condition which is we only need for this type of so-called generalized fractional derivative. Sorry, happy to you, but that's exactly the answer here. So you consider Lévy measure of subordinator and tail of this measure. So measure of something from x to infinity, and that's exactly the form of this kernel. For inverse stable subordinators, that's t minus s to the power minus alpha, and in general, this could be any function of this type. So infinitely many subordinated, infinitely many possibilities. But
okay, sorry, can I disturb you, Trifce? Sorry.
Sorry.
Okay, Nikolai, Katarzyna Gorska from Krakow. I have a question for you, because I suppose that it is very important that our subordinator, our memory subordinator is a infinite divisibility function.
Yes,
because
I mean,
yes, because it's related. I have a feeling that it is related with causality.
Yes, but I mean, of course, all subordinators are related to infinite divisible stochastic processes because of that's Lévy processes. But
you can choose any memory kernel which is the sonic, which is a sonic pair, which satisfies the sonic equation.
That's one possibility. People popular is to use sonic pair, so-called, which are related. That's a one possibility. But of course, one can consider another possibilities. For instance, I have a paper so-called Dichmann subordinator, and
Okay.
and you can find in this fractional calculus journal, and which is again gives a complete, not complete, but one of possibility when we ignore big jumps, only to consider small jumps. That's exactly Dichmann subordinator. For instance, it's not Sonin, doesn't belong to Sonin kernel, but we can build a theory with this. If you send me a mail, I can send you this paper, basically.
Okay. Okay. Thank you. Thank you. I'm sorry, Trifte.
Oh, sorry, I interrupted. We have to ask.
Sorry.
We are not main people here. Okay, sorry. Okay, that's
sometimes it's a matter of how you call it, some procedure or some, for example, in physics, we like to use this subordination. Maybe in mathematics, there is a different approach, but the idea is the same. And I just wanted to say that you can use a memory kernel of such form that there are some restrictions. It should be a completely monotone function, and the Laplace transform of the memory kernel multiplied by the S in Laplace space should be a Bernstein function. And with this, you are sure that the solution of the corresponding this generalized diffusion equation will be non-negative, that we will have a good stochastic process. So, but also, as you explained, there are different ways of interpretation and explanation of this subordination approach. And the second question related to the stochastic resetting, yeah, there are many different resetting mechanisms. There are papers, for example, when you reset the particle not to the initial position, but to some other position, or there are some papers in which you have a resetting to a random position. So all the time you reset the particle to some random position. Or there are papers in which you don't use, for example, exponential distribution of the resetting events, but you use a power law. Or you can use a resetting with, I don't know, with finite velocity, or you can use partial resetting. So there are very different mechanisms, or you can use sharp reset, which means that you reset the particle to the initial or other position always after same time. And the corresponding behavior, it's a different, but for example, for a power law resetting, then you have regions of the parameters of this power law resetting in which you will observe saturation of the mean square displacement, or you can have a time dependence of the mean square displacement. So there are very different mechanisms of stochastic resetting, and this is a very, very popular topic nowadays.
Thank you so much.
More questions? You can unmute your mic and go for it. Yeah, I have one question. So on slide 17.
17.
So yeah, so this equation is for a particle that is embedded in a fluid, right? So with that regards, I mean, if the particle is of a reasonable size, then you have to take an integral of all the collisions with the fluid, and that will be the net effect. So have you considered that when coming up with this equation?
For this case of a shear-driven diffusion, we just consider the simple Brownian motion with a linear shear flow, and then we just introduce this waiting times, and then we introduce stochastic resetting. And if we have these mechanisms, then we can analytically analyze the mean square displacement, the variance, the kurtosis, all these parameters from which we can conclude about the distribution of this new process. But I'm not sure about your.
So you consider that the particle follows a trajectory which is akin to Brownian motion, not that
the particle performs Brownian motion, but here we additionally have this shear rate here, constant shear rate, which is along the x direction and changing with y direction. And this is exactly solvable model. Maybe this can be generalized to not just to this two-dimensional flow, but three-dimensional flow and some other cases. But we just started last year with this process, and we still investigate it.
So that consideration to me looks linear. So I'm not. So I would rather not talk about turbulent diffusion, but I would rather talk about laminar diffusion, which has molecular diffusion in it. Because
okay. But in some papers that this equation was considered, that they said that it's like a form of turbulent diffusion, just because of this mean square displacement grows very fast. It's T to power 3.
I'm still a little uncomfortable with the terminology, but I understand what you guys are doing. But because when you talk about turbulence, I mean you should have non-linearity, which is the
right
source of turbulence, and
right. You are right.
And non-local and there is molecular diffusion, which the diffusivity constant has a physical interpretation. When you talk about turbulent diffusion, you might want to then one talks about diffusivity being non-constant, and that is a model and not actually a physical physical thing. So and that construction is more like a non-Fichtean diffusion term, where you have a non-constant non-constant diffusivity term. So just a little bit on the terminology.
Right. But I will be happy to read some of these words that you mentioned.
Probably I'll send you one of the papers.
Yes, please. Thank you.
Papers on it. That would be okay. Secondly, I like the telegrapher's equation where you had a two-time derivative. So both of those derivatives were actually fractional, and so I wanted to understand if there is a paper where you have one integer order term in time, and the second term is a fractional derivative. Because I'm not acquainted with that line of research, because I don't really solve those equations.
Yeah, I think that there are some models in which you have maybe different fractional derivatives, not mu and 2 mu, and maybe some ordinary derivatives, some fractional, but such equations, we cannot derive such equations starting from this continuous time random walk model. So there are different approaches to these equations. Yeah, there are some papers I can share some with you.
Yeah, that would be very nice.
Yeah, but the approach of derivation of this equation is different than this that I show you here.
Yeah. So the reason I was asking, because when it comes to particles embedded in fluid, there is something called as the Maxey-Riley equations in the 1980s. And they derived an equation which had exactly this term, a half fractional derivative in time and an integer order time.
Okay.
Yeah. Okay.
Thanks.
Are there more questions or comments? You can unmute your mic. Okay, I believe there are no questions or comments, so this is a good point to close this talk here. And thank you, Trifce, for the very nice talk, and it did instill a very good debate and an academic exercise. So we are very happy to have you here, and especially on this 50th seminar occasion. Thank you very much.
Thank you very much for the invitation.
Yeah, you're welcome.